Before we welcome the guests of the next event, on behalf of the organizers and co-organizers, I would like to thank all the scientific institutions of Trieste, City of Knowledge, as well as the institutions that collaborated with us. A special thanks goes to the festival's main partner, the partners and content partners for their crucial contributions. Thanks also to the media and technical partners. Lastly, a heartfelt thanks to the 200 volunteers who made this edition possible. One final note. I'd like to remind you that the next session will last 75 minutes, with the final 15 minutes dedicated to your questions. Please also remember to check the updated event schedule on www.triestenext.t, which you can access via the QR code. Enjoy the event and have a great festival.
Good afternoon to everybody. Welcome to this session dedicated to volcanology. The mean we have to speak with inside of with the heart of our planet. My name is Franco Zanini. I graduated in physics in Trieste, then I specialized in executive data science at the Johns Hopkins University and in volcanology at the LMU University in Munich. But my business is to be a researcher at Elettra Sincrotrone Trieste, where I arrived from the University of Wisconsin, where there was another synchrotron. My main activity is analysis of cultural heritage, but today we will speak about volcanology. I also teach chemistry of cultural heritage at the specialization school in archaeology, ruled by University of Trieste, Udine, and Venezia Ca' Foscari. Before passing the microphone to my colleagues, just a very short introduction. Okay, first of all, why do we study volcanoes? Volcanoes are what we call messengers from the deep. They carry an enormous amount of information about the depths of our planet to the surface of our planet in very short time and in very fresh conditions. So we can examine them immediately after their arrival on the surface of the Earth. Volcanoes are an essential part of the way our Earth has evolved over time. And this is due both to the action of volcanoes and the fluid system below them, so the so-called magnetic system, which is largely divided in different geochemical reservoirs, which divides the surface of the Earth in different situations. Volcanoes are always very important in our evolution. It's very likely that the heat and the particular chemistry that was provided by volcanoes and the volcanic environment on the surface of the Earth has been vital in defining the condition for the evolution of life, both our life and the life of the whole system. If we move rapidly forward the very recent past to our human evolution, there is a clear evidence that human evolution probably arose in volcanically active regions, that the individual aspects of volcanic activity impacted human evolution again and again in its early stages. Okay. It's also very possible that volcanoes have been responsible for the extinctions of certain forms of life in the history of our planet. The diagram in this image shows an estimation, if you will, of biodiversity in the geological past of our planet. And you can see there are several drops in the presence of life on our planet. If these data are correct, this is based mainly on the study of fossils, it means that the extinctions of large numbers of species on the surface of our planet has been a recurrent event in the history of the Earth. There are several proposals for this, but maybe the most important ones say that individual cases of catastrophic species decline are related in time with the observance of major volcanic activity on Earth's surface. Just to remind the history of dinosaurs, for example. From the very geological past, so millions of years, let's go immediately to recent years, so the last centuries. If you look at the diagram on the screen, you'll see a plot of the number of fatal eruptions divided by century. This means that the number of eruptions which have been recorded, which are known to have caused human deaths being for centuries. You can see this curve rises very steeply from the left to the right. Cosa? Ah, sorry. Questo non funziona. A very steep rise, you can see, going from the 14th century to our times. This is not due to a better measure of recordable increases in volcanic activity in this very short amount of time as compared with the geology of our planet. It is due to our population growth and all the encroachment, the impingement of these very fragile areas of the surface of the Earth, which are regularly visited by volcanic catastrophes, which means that people is aggregating, is going forward volcanic regions for a lot of reasons, because the Earth is better, because the weather is better. But this forces a series of important issues you have to face now in related areas of planning, of politics, of environmental policy. And all these things ultimately are translatable into economic impact, which is very strong, and how a society is led forward. As a consequence, it's becoming more and more important to try to understand and to reliably forecast what a volcano in a particular place with a human population around is likely to do within a certain time frame. In this session, what we will do is to have a look on how synchrotron radiation facility can help in this study, help us to understand not yet when a volcano will erupt, but in which way it will erupt. There is a big difference between a diffuse eruption and an explosive eruption in terms of effect on the life of people, on the destruction of a structure, of human structure. Near me, there are some of the best possible scientists which are entitled to speak about this topic. The first one I'm going to introduce is Lucia Mancini. Lucia Mancini is a material scientist physicist specialized in imaging characterization of materials since 1992. She earned her PhD in physics in Grenoble, where she worked at the synchrotron for 5 years before coming to Trieste, where she was a colleague and a friend for over 20 years, where she was responsible of a microfocus X-ray computer tomography lab and collaborated with, I think, hundreds of different institutions. Since 2022, she's a senior researcher in Ljubljana at the Slovenian National Building and Civil Engineer Institute. She will give an introduction to advanced X-ray imaging in order to reveal hidden features not only in volcanology, but in general in stones, in geological materials, and how is it possible to extract quantitative information from these images. Lucia, the floor is yours.
Okay. Thanks so much, Franco, for this nice introduction. Oh, sorry. Okay. So I will try to introduce you some of the X-ray imaging techniques that we used in the past years to study geomaterials at Elettra, but also in other facilities, thanks to the large collaboration that we have in this field. The technique that I will focus on is X-ray computed tomography. That is a technique well known in the medical field, but can be used as a very important non-destructive tool, imaging tool, to investigate the external but also the internal features of objects without necessity to section or to treat this object. So it's very important because allow to study samples in not only in a non-destructive way with the same technique, but also after to study them with the complementary techniques to extract complementary information, like also chemical, structural, and so on, but also to perform the so precious in situ experiments. This means experiments under dynamic conditions, like thermal treatment, mechanical testing, and so on. This is the well-known instrumentation for clinical CT, but there are many other types of instruments for computed tomography. We will focus in particular on microtomography, allowing to study samples with spatial resolution, so visibility of details at the micron scale, so 1,000 times less than 1 millimeter. And so this means that you can use a different instrument in this scale. Some of them are laboratory or on the industrial scale, but the most beautiful, let's say, and highly informative images can be obtained with synchrotron radiation. And this is an image of the synchrotron where I had the opportunity to work. The first one is the synchrotron radiation facility in Grenoble in France, and the other one is the Elettra facility in Trieste. And in both this synchrotron and also in many other synchrotron, as also my colleagues will show in their talk, it's possible to perform imaging experiments with different characteristics depending on the facility. But these techniques are really nowadays precious and highly demanded. Synchrotron radiation is generated thanks to charged particles, electrons in particular, that are traveling at a speed very close to the speed of light in a circular path. That is the typical shape of synchrotron radiation facility that you can see here, but you can see also in other synchrotrons, and thanks to this, say, working principle, it's possible to have to extract a very focused and highly intense X-ray beams that can be used for also for many other techniques, but in that case, we speak more about imaging. And there are many laboratories in each synchrotron facilities, each one devoted to a technique. And we will focus on the CIRME beamline, in particular, that is the beamline devoted to imaging in at Elettra. Synchronous radiation allow to have unique features for imaging, in particular very high flux, very high intense X-ray beam that allow to study samples with a very high spatial contrast and temporal resolution. This means that it's possible to perform experiments with a resolution that is not achievable with other instrumentation, and also to see objects that have a very low difference in contrast that are not distinguishable with other tools, but also to perform very fast dynamic experiments in order to investigate some property under some dynamic treatment, like I said before, thermal or mechanical, and my colleagues will show some examples. Another unique feature that is exploited is the so-called phase contrast technique that is really easy to implement, to use with synchronous radiation. And here you can see two images that as an example, just to show you how it's evident to obtain a better and finer contrast in an image thanks to this technique. Here you have a mimosa flower observed in the normal absorption image. That is a normal radiograph, the same that you will have in the hospital in case you have a broken arm or something like this. But the same object visible with the unique features of phase contrast imaging. You see the amount of details and that you can see and how well you can see the object. And this is exploited in many, many different fields, from medical, biology, geology, and so on. Yeah. And so, together with this type of techniques at Elettra since 2005, researchers in the imaging field have also combined these unique techniques with synchronous-based imaging with also advanced laboratory techniques. And this in order to enlarge the scale of studies, of samples, and spatial resolution that can be achieved. And several instruments are available in Trieste or in the synchrotron also for that purpose. But how it works? So you have an object, this is a coral, for instance, you rotate the object inside the X-ray beam, and you record the many radiographs with the digital detector. And these radiographs, after with the mathematical algorithms, are reconstructed in order to see the internal features of the object. So different section, virtual section, without cutting the object, to see how the object is internally. And it's also possible to have a model, a 3D model of the object once you have reconstructed with tomography. It's not only possible to see the external wall part of the object, but also to see internally how the features are distributed. In this case, pores, for instance, this is a stone, a volcanic stone. You see how well you can see the size and distribution and connectivity of these pores inside the rock. And these are highly informative to study different type of phenomena, and can be applied, of course, in many different fields, as I said before, from biological, medical, building materials, archaeological sciences, and volcanology. What is normally done is not only to have beautiful images that are, of course, very important from a visual point of view, but what is very important in the experiments, as also my colleagues will show, is to extract some quantitative information from these images. And this is done with the special software that are devoted to the analysis of 3D images that allow to extract quantitative parameters like porosity or size of the pores or size of crystals. Anything that is interesting inside your object can be quantified. And these software are various, can be commercial or research codes, and can allow with mathematical tools to extract this information. And this information are used to study, for instance, volcanic rocks. And these volcanic rocks are complex materials, complex multi-phase materials with glass matrix containing pores that are called vesicles in volcanology, and crystals of different nature. And these kind of materials can be studied with imaging. And sometimes these images are very difficult to analyze because the object can be very close in mass density or and to be distinguishable. And this, I will show just an example of this. I have 1 minute, 2 minutes, okay, yeah. So this is a sample, again, a volcanic rock that was observed before by electron microscopy and contained some crystals, small crystals embedded in the matrix, that is a glass matrix. And this, when we did experiments on these samples with phase contrast imaging, we couldn't see anything inside. So just the matrix, more or less. After we applied some mathematical algorithms, these software tools that I showed before, and if you look at the zoomed image part of this crystal, you see that you can visualize, discriminate these crystals finally from the matrix. And thanks to this, after it's possible, thanks to the fact that you have many sections of the object, so a 3D image of the object, you can visualize them and extract from the matrix these crystals. And if you look at one of them, you can see, for instance, how it's done in 3D, virtually extracting from the stone. And you can analyze, of course, the shape of these lamellae that are crystalline lamellae, their orientation, the mutual distribution with respect to any direction of interest. And this is also, again, very important for volcanologists and geologists in general. And the last important application of imaging is in the dynamic case, not only in the static condition as before. And in our synchrotron at Elettra, we did the pioneering studies in the field of geomaterials. And since, let's say, 2009, we started to do dynamic studies. And this is an example of what you can do. So treating the sample at high temperature, up to more than 1,000 degrees, to simulate a volcanic eruption, you see that each of these images is a 3D image, a different moment of the thermal treatment. So you can simulate what happens in the first seconds of a volcanic eruption and to see how the rocks are evolving. And my colleague will show more examples. And at Elettra also was implemented a particular furnace to study this type of studies. And this is can be used by the users for this kind of experiments. This is just an example, but of how the rocks are behaving during volcanic eruption. So there is the expansion of the rock, the vesiculation, and the, let's say, explosion that can be more or less strong. But yeah, I can do faster because, yeah, you see. And that's all. I hope that this was clear enough. And after my colleague will show how this is applied in more sophisticated example and cases. Thanks so much for your attention.
Thank you, Tia. The speaker is Fabio Arzilli, colleague and a good friend of mine. He's a neuroscientist by education, and he became an experimental petrologist and volcanologist in recent years. Now he's a researcher. Sorry. And his research focuses especially on the role of crystallization and degassing in controlling magma ascent dynamics. Today, he will show us an experimental approach designed to combine high pressure, let's remember we're speaking about gigapascal of pressure, and temperature of thousands of degrees, and combined with X-ray microtomography in order to study the evolution of magmatic processes in 3D. Fabio?
Thank you, Franco. Good afternoon, everyone. So my talk is focused on a new vision of volcanic processes in real time. And particularly, so we have a volcano with the magma chamber beneath it. And before the eruption, magma can be stored in a magma chamber at high temperature, high pressure. The pressure is related to the depth. So magma chamber can be at several kilometers beneath the volcano at high pressure. And during the eruption, magma can rise up and then goes up to through a conduit to reach the surface and feed eruption. So there are two main processes that control the style of the eruption. One is crystallization. So magma can crystallize and form minerals. And the second one is the gaseous solution. Magma can contain a lot of water and CO2 into the magma chamber, okay, here. So, and during the ascent, basically moving from deeper depth to the surface, we have a decompression. It's like to open a Coca-Cola bottle or champagne or Prosecco. We see that the CO2 will basically form bubbles, form foam, pushing the liquid outside of the bottle. This is the same. Magma can contain a lot of water and CO2 under pressure. As soon, so we open a path toward the surface. So vesiculation, that is the process. So the gaseous solution will occur and a lot of bubble will be formed. Okay, so crystallization and gaseous solution control the style of the eruption. So, and we have a different eruptive style. So we can go from highly explosive eruption, like a Plinian eruption, the example of the 79 Vesuvio eruption, to less, in this case, this is the highly explosive eruptions where magma can be erupted and can reach 30, 40 kilometers in the atmosphere. So, and then we have less explosive eruption like lava fountaining, where magma can be ejected at several hundred meters above the volcano in the atmosphere, or lava flows, for instance, that are effusive, they are degassed, basically. The magma lost the gas completely. And what we can observe is the product of this eruption. We can observe rocks, okay, that is magma solidified. And we can study the textures of these rocks and what they record. So the bubbles form, like in this case, you see large voids, large bubbles. Here you can see tiny bubbles. So these processes control the eruptive style, and the rock will record the gaseous solution and crystallization. So, but we don't have we don't have access to the inside of the volcano, so we cannot go there. We cannot see these processes in real time. So the unique way to study these processes is to look the rocks. Today, I will present a way to reproduce magmatic condition in the magma chamber and the conduit and look the processes in real time. And we can do this in the lab. First of all, I want to introduce what magma is, just to be clear, that magma is a liquid rock, okay? And is a multi-phase material composed by a liquid silicate melt, gas bubble, gas, water, CO2, and crystals, okay? Magma can form different silicate minerals. This liquid magma at depth can be transformed a rock during the eruption, solidifying. So it will cool down, and this liquid will be transformed in a glass. At the end, we have a volcanic rock. So the best way to study this multi-phase material is to use, as Lucia presented before, X-ray tomography at the synchrotron, for instance. So what we can observe is the distribution of the bubbles or vesicle, as you prefer, and the distribution and the size of the crystals in 3D within this rock. So therefore, we can quantify the connection of bubbles. So quantify the connection is really important because we can understand if the gas can escape from magma or can remain trapped. And this controls the intensity of the eruption. And then we can quantify the size and the abundance of crystals. So the more magma will be crystallized, the more the less the mobility will be. So like the example water and liquid water and frozen or almost frozen water. So the liquid water will flow easily than an almost frozen water nearly to ice. So now I show you how to combine X-ray tomography with high temperature, high pressure furnace in order to reproduce magma chamber and conduit and to visualize the processes that occur within the magma chamber and the conduit. So here we use an high temperature furnace that there is two windows in order to allow the X-ray beam to pass through. The sample will be here, will be heated using an heating element. And then we have a system to pressurize the system, the pressurized magma. And this we can simulate quite shallow conduit conditions. And what we can do, playing with temperature, we can induce crystallization. This is a magma from Etna that crystallizes this mineral through time. And we can control and we record the process in real time. Here we can see a video that this video summarized 90 minutes of experiments. So crystals can form in 90 minutes, for instance. Here you can observe the evolution of a single crystal. So to study the kinetics of crystals is really important because it can give us the time scale of the processes within the reservoir and conduit. So then we can also increase the pressure with this other new system. And with this system, we can investigate a wide range of conditions. So from the magma chamber to the surface. We can play with pressure. So it's like simulating an ascent of a magma ascent from deeper depth to the surface. And what we observe is if we change the pressure, gas will dissolve. And we can see the formation of bubbles through time. And we can see also this directly in 3D. And this actually we are simulating magma ascent from a magma chamber to the surface. We are simulating eruption. So basically the travel of magma through the conduit during the eruption. And what we can quantify is how fast the bubbles connect each other. And we can see that the connection can occur in terms of a few seconds. So therefore, the connection means that if the gas is able to escape from magma or remain trapped, if they remain trapped, means that magma will store a lot of energy, causing a highly explosive eruption. If the gas will escape, we will have effusive or less explosive eruptions. So, and this process can last a few seconds. In a few seconds, the eruption can shift from highly explosive to effusive, for instance. So to summarize, basically, I introduced two main processes, crystallization and vesiculation, that control the mobility of magma and the explosivity. And this can help us to understand how volcanoes can shift from an effusive eruption like this lava flow to mild explosive eruption like lava fountaining to highly explosive eruption that can be catastrophic for society and for cities. So, but to study this more in detail and to better understand the physical processes, we need to link the experiments in 4D with numerical modeling, simulating basically the magma ascent through the conduit, considering fluid dynamics. So the next two talks will present this aspect. Thank you very much.
Thank you, Fabio. Thanks for the of the problem. Giuseppe La Spina got his PhD at the Department of Mathematics at the University of Pisa, and now he's a researcher at the Istituto Nazionale di Geofisica e Vulcanologia in Catania. His main area of expertise is the mathematical numerical modeling concerning the physics of this topic. And his work not only contributes to understanding of volcanic phenomena, but also physical and practical implications for the risk management associated with volcanic eruptions, the problem we were speaking at the beginning of our meeting. He will speak about volcanic eruptions and how single processes influence the eruptive style of this phenomena. Mathematical modeling is the fundamental tool that Giuseppe is using to describe this interaction. Please.
Thank you, Franco. So, as Franco said at the beginning, the volcanic eruption are very important and played a fundamental role in shaping the surface of our planet. They are very dangerous and frightening events, but they are really also amazing and fascinating natural phenomena. Here, I show you two footages. On the left, we have some eruptive activity from Etna, it's a fountaining activity. On the right, instead, we have an eruption from La Palma in Canary Island. And here you can see the different style of activity that we can observe and the hazard that they can pose to the people. Indeed, across the world, there are millions of people living nearby a volcano, and eruption pose a real threat to people living nearby the volcano and to the surrounding infrastructures. Okay. And volcanic eruption, however, can also affect the people living far away from the volcano. Everyone probably remembers what happened in 2010 with the eruption in Iceland, Eyjafjallajökull, where this volcano emitted a very strong ash plume, which covered most of Europe, causing the air traffic to be completely stopped and causing a loss for more than 2.5 billion euros. So to understand and try to predict the evolution of an eruption is fundamental to understand the dynamics which occurs during magma ascent. But what is magma? Fabio already started to mention about this. Magma is a molten rock which ascends from depth towards the surface. Basically, it's a viscous fluid which contains small particles, which are called crystals, and bubbles made of different gases. They form and grow with time during the magma ascent. And as magma ascends, the pressure decreases, and eventually it accelerates until it exits from the vent of the conduit. Here is a schematization of what is happening. So we have the white circular bubbles, and there are particles inside. We can see these are growing while ascending. But what causes the increase in bubbles and crystal? There are several processes that are happening during magma ascent. So we said we have a crystal formation and growth, bubble formation and growth. We have variation in pressure, temperature, and viscosity of the magma. We have gas escape through the conduit itself towards the surface or laterally through the volcanic edifice. And we can also have magma fragmentation. Basically, at a certain point when the conditions are met, magma stops to behave as a fluid and starts to behave as a rock. And basically, it fractures. So the physical properties of magma are really important, and they affect the volcanological processes that can happen during the eruption, and they affect the volcanic behavior of a volcano. There are several styles of activity, but we can distinguish that the main one can be summarized in four categories. We have explosive eruption, in which we have a strong ash plume, which is emitted from the vent of the volcano, can reach up to 10, 20, 30 kilometers in height and create an umbrella cloud. This is an example from Calbuco, an explosive activity in Calbuco in 2015. Then we have effusive eruption, where magma is pouring down from the vent of the volcano, causing this lava flow. This is an example of Nyiragongo eruption in Rwanda in 2021. We have a fountaining activity in which magma is ejected from the volcano as a molten rock, so it's really fluid. We can see these curtains of fire, basically, which are ejected at high velocity from the vent of the volcano. sometimes, like it happens on Etna, it can create also an ash plume from the top of the fountain. And then we have the strombolian activity. This is a very peculiar eruptive style in which we have large bubbles that explode at the surface, creating this sputtering of magma that are ejecting across to the vent of the volcano. This is very peculiar for Stromboli, but there are also evidences in other volcanoes. So what affects the style of a volcano? There are several factors. Mainly are three factors that affect the style of activity. We have viscosity. Viscosity is a measure of the resistance of a fluid to flow. If you want to really summarize and simplify, an increase in viscosity leads to an increase in explosivity of a volcano. And viscosity is affected by the composition of the magma, the temperature of the magma, the presence of bubbles and crystal, their shape. So all of these can affect how the viscosity is changing while magma is ascending. Then we have outgassing. Outgassing is the process by which gas is lost from a material, in our case, from magma. And again, if we want to really simplify, an increase in degree of outgassing leads to an increase in effusivity. So magma loses its driving force, gas is lost and tends to erupt effusively. And outgassing can occur due to two principal processes, basically buoyancy, due to the fact that the gas is lighter, less dense than the magma, and due to permeability, which is the formation of permeable pathway through the magma and allow the gas to go through the magma itself. And then we have the magma ascent rate. The magma ascent rate basically is a measure of how quickly magma ascend in the conduit, and this is a proxy for magma velocity. And again, we can relate an increase in magma ascent rate to an increase in the fountaining activity or in the explosivity. And magma ascent rate is affected by the pressure of the magma, the depth, the radius of the conduit, but also viscosity and outgassing. So as we saw, all of these processes are happening during magma ascent, and they are all interconnected and they are happening all at the same time. So trying to predict the behavior of a volcano is really complicated. And so mathematical formulation, numerical modeling can help us on this really difficult task. Indeed, through mathematical equation and numerical modeling, we can solve for all of the major processes happening during volcanic eruption, and they can help us to understand the overall dynamics and eruptive behavior. So what we usually do, we start from a schematical and theoretical approach of our process, in this case of the magma ascent in the volcanic conduit. We convert this into an equation, a mathematical formulation in terms of system of equation, and then we solve this equation with numerical modeling, and we extract statistics from this numerical model, and that can help us to infer the style of activity in the specific case. This is an example from Etna. But numerical modeling is a very powerful tool and can help us to constrain the eruptive behavior of a volcano, but it's fundamental that this is constrained by field observation, analytical measurement, and laboratory experiment. So what we usually do, we usually go to the volcano, we collect sample, we analyze this sample in the lab. We do, for example, we bring the sample in the tomography, we do X-ray tomography, we extract quantitative information from our samples and data, and then we use this to infer the numerical model, and we extract then some quantitative information and some statistics. But so it's fundamental that the model is driven by observation and data from the lab. And this is exactly what we did in this work that Dr. Bamber is going to show us more detail of. And that's it. Thank you very much.
Now, welcome, Emily. Emily Charlotte Bamber got his PhD in Earth Sciences at the University of Manchester. and now she is a postdoctoral researcher at the University of Torino. Her research takes a multidisciplinary approach, so combining together everything we've seen until now, the contribution of our three colleagues. So she combines the observation and analysis of natural samples ejected during volcanic eruptions, synchrotron-based X-ray imaging techniques, and numerical modeling of magma ascent processes. She will describe the application of X-ray imaging and numerical modeling to investigate outgassing behavior during, in this particular case, highly explosive basaltic eruptions. Emily, floor is yours.
Thank you. So what I'd like to present today is a specific example of how we can use all of these ideas, these methods that we've discussed to investigate a particular problem in volcanology. And in this case, this is outgassing behavior during highly explosive volcanic eruptions. And what we mean by this is how does gas behave during magma ascent, and how might this change the eruptive style of a volcano and what we observe at the surface. So to do so, first what we did was we went to the field to collect natural samples of a past volcanic eruption. And here, this photograph on the left shows an image of a deposit of a past eruption from Messiah volcano in Nicaragua, which is an active volcano located in Central America. And what we see is the sequence of fragmented material. This is pieces of small fragments of rock. And what this represents is frozen pieces of magma. What we can do is we can collect samples of these. These are called volcanic clasts. And what we can do is use this information to look at the crystals, the bubbles that are present within these samples, and how this might tell us information about what's happening at depth within the crust beneath our feet. We also looked at Mount Etna, the volcanic system located in Italy. And what we can see here also is that this deposit can occur on features of the volcano itself. And here in the volcanic cone, and you can see all this black fragmented material at the bottom is what's left behind after a previous volcanic eruption. We can then take these samples back to the lab, and then we can look at these with several techniques. What we have here is a microscope. We can take our samples, and we can look at these with very high magnification. So we're able to see the very small crystals and bubbles within inside the sample that you might not necessarily see just with your eye in the field. We can then use several pieces of equipment just to look at also the chemistry of this rock. So what is this rock made from? What is its composition? And how the concentration of certain elements such as maybe iron, magnesium, what this might reflect about how this rock formed. And this is also important information for us. And we can also take images of these samples and look at the crystals. This is an example of one of these images. And what I would just like to focus on here is how we can look at these crystals and bubbles, which are indicated by the red arrows, and how these very small features inside the rock can tell us about larger processes that happen at a volcano. The scale bar in the bottom left of the image is actually a fraction of a millimeter in size, if that gives an indication about how small these features are inside the rock. What this allows us to do is to reconstruct what might be happening at depth, so a few kilometers beneath the surface, and what might happen as magma travels from depth to the surface during an eruption where we can collect this material. But what we're also interested in is this path that magma might take from depth to the surface. To do so, we're also interested in how these features inside the rock might be connected in 3 dimensions. Therefore, X-ray computed microtomography is a very important technique for us because this is a non-destructive technique. We can take our samples there to the synchrotron, and then we can also visualize them in 3D. These series of photographs show exactly what we did with our samples we collected from the field. We placed our sample on a stage, and we allowed rotate the sample so we can see all the way around the sample. The setup was performed at Elettra Sincrotrone Trieste using our samples from Messiah. The X-ray beam then passes through the sample, and depending on what is inside that sample, it might respond differently. This is collected by the camera at the end, and it allows us, using computer-based software, to reconstruct what this sample looks like in 3 dimensions. So where do the bubbles occur? Where do the crystals occur? What they might look like, and how they're also connected to each other. So in this particular example, what we're interested in is how gas bubbles inside the magma, how they're present and what influence this might have on how the magma behaves. But what exactly controls how gas bubbles can move and how gas can flow through the magma? The number of bubbles. So the number density is just the number of bubbles within a given space. So how many bubbles are present within our sample? We can also look at tortuosity, and this is a measure of how irregular a flow path is, the shape of it. So is it wavy? How far does this deviate from a straight line? We can see an example here from this wavy curved path that passes through bubbles. As it becomes more complicated in shape, it's harder for gas to flow through. Finally, we can also look at the size of these paths, these connections between 2 bubbles. If a path is narrow, is small in size, it might be harder for gas to pass through. All of these information requires 3D information, which we obtained at the synchrotron. So these are actual images of my samples that we observed in the first slide from Messiah. On the right, highlighted in white, are what these bubbles look like inside the sample. We can already see that these samples are from a highly explosive eruption, and they actually have a large number of bubbles, that they have these irregular shape paths which connect them, and they're also small in size. So in this case, it might be difficult for gas to flow through our sample. We can also look at Etna. So in the case of the highly explosive eruption, which is what we see at the top row there, is that there is still a high number of bubbles, and these paths are narrow and irregular in shape between them. But what we did for Etna is we also wanted to look at samples of non-explosive activity. So how does this change based on the behavior of the volcano itself? Underneath are images from a sample of the Etna 2001 eruption. This is a lava fountain or a lava flow, so a much different type of activity. And you can see, just looking at the images on the right, that the bubbles look very different. They are much larger in shape, and there's much fewer of them. And they also have more regular paths between them. We can also look at how much of this space is connected. The purple highlights how these bubbles are connected. So they become more connected, passing from the left of the image to the right. And we can relate this also to the amount of crystals that are present in our sample. So just focusing only on the number of bubbles, we find in general that our samples have a high number of bubbles, and they're actually higher than the majority of non-explosive activity. This is highlighted by the orange circle. So your typical activity from stromboli or lava fountains as well. But we also see that high-intensity lava fountains, in this case, I mean lava fountains that can reach hundreds of meters in height, such as the Etna November 2013 eruption, these also have a lot of bubbles. What this tells us is that the textures and the features we observe in our samples might be connected to what we observe at the surface. But to relate this to a physical process, we can also use numerical models. This graph here just shows the results of performing a lot of simulations with a computer to allow us to pick out trends. So on the left panel, we can look at how the number of bubbles might influence the amount of explosive eruptions we observe in our results. And we see that as there is a high number of bubbles, we have more explosive results. Instead, for tortuosity, so there's a regular flow path, as this increases, we also see an increase in the amount of explosive eruptions. Finally, the size of the flow path between bubbles, as this becomes more narrow, we might have more explosive eruptions. We also can plot our data, and we see that our data also agrees with this from our natural samples. So combining several techniques can provide us a lot of information about what a volcano might be doing. So putting this all together with this diagram here, we can look at how what's happening at depth within the crust and the magma's flow path to the surface, how this might relate to explosivity. So with a lava flow, a more traditional and lava fountain where there's a few tens of meters in height, this might be driven by a high temperature magma, so a very hot magma with a small amount of crystals and bubbles. As magma starts to rise faster speed to the surface, it might eject the vent or be erupted at a much higher speed and reach a much higher height above the volcano. Finally, for a highly explosive case, what we might see is a high number of bubbles, but also a cooler magma with more crystals. This may produce a lot of ash and an eruption column that exceeds tens of kilometers in height when it is erupted, with a significant impact on the hazard. So to conclude, to summarize everything we have discussed today, volcanoes do show a wide range in eruptive style. So for example, we can see lava flows and lava fountains, such as the photograph here, which shows the 2021 eruption of Etna in Italy. And this illustrates the progression of lava flow down the flank of a volcano. We can also see these lava fountains become more intense. So lava is ejected at a much greater height from the volcano itself, such as here for the photograph of the La Palma 2021 eruption. Instead, this might transition into something that is a lot more explosive. So a production of ash, pieces of rock that might be distributed kilometers away from the volcano itself. What this illustrates is that because we see a wide range in eruptive style, is that there is also a wide range in the impact of a volcanic eruption. So for example, they can produce thick sequences of ash that is then deposited on roofs or roads or in water sources, which can contribute to a significant challenge for people who live nearby the volcano itself. The image on the right is actually of Grindavik, which is located in southwest Iceland. And this is the 2024 activity. What this shows is also lava flows and lava fountains can cause a lot of disruption, leading to evacuation or damage to infrastructure such as roads. Additionally, these processes can cause problems for aviation in the cancellation of flights or closure of airports during an ongoing volcanic eruption. So therefore, it's important to understand the eruptive style that might occur at a particular volcanic system and how this might impact what we observe at the surface and also the hazard. So to summarize, how can we investigate the impact of a highly explosive eruption? We can use several techniques. We can go to the field. We can collect samples of past volcanic eruptions to understand what a volcano may do today or in the future. It's also important to understand what it has done in the past. We can collect these samples of past activity, and we can take these to the laboratory. We can look at the chemistry, what they're made from, but we can also look at what is inside in terms of the crystals or the bubbles, what they might look like, how many they are, and how this might relate to the behavior of the magma itself. We can then expand this analysis. We can take samples to synchrotron facilities, and we can use techniques such as X-ray microgravity technology. So we are able to see our samples in 3D. So how these features might be connected in the sample and how they might be distributed in 3D space. However, to understand all this information from natural samples, we need to understand how they might have formed. For that, we can return to the laboratory and we can perform experiments. So we can start to form crystals and bubbles in the lab to see what temperature, pressure they might have formed under, and what this can tell us about the history of the natural sample that we collect in the field. Finally, we can use all this information together to start to connect this to a physical process, such as what does magma do when it ascends from depth to the surface. For this, we may need numerical models. This allows us to simulate magma ascent and the processes which might occur as magma ascends to the surface. This is constrained using all of our analytical and experimental data. So overall, we can use a lot of techniques to investigate the eruptive style and impact of explosive volcanic eruptions. Thank you.
Now we have time for questions from the audience. If somebody is interested to some more information about what's happening behind our feet. Good question. Emily.
It's a great question. I think future direction may be to look at combining all these techniques and how this can give us real information during a volcanic eruption as it is ongoing. So being able to collect samples, analyze those in the labs during an eruption that might be happening over a long period of time. A few examples of this are the La Palma eruption and the activity that you may or may not have seen in Iceland this year. These occur for months at a time. So being able to provide information fast that is also useful for managing an ongoing eruptive crisis can be really important for managing the impact. And I think some of these techniques here can provide useful information for this purpose.
I have a question myself. You showed that the same volcano can behave in different ways in different periods of its life. Why does this happen? A lot of people think that a single volcano always behaves in the same way. It's not true.
No, this is correct. Yes, a volcano might show a wide range in the eruptive style or the explosivity during its lifetime or its period of activity. What this might represent is changes in what's happening beneath the surface. So processes that might change in the magma reservoir. So we might see magma cool down or form more crystals. This might have an impact on then what we observe at the surface. An example of a volcano that you may know that does show a wide range in eruptive activity is Etna, where there is a considerable variation in how many lava fountains occur within a given period, how high they are, how intense they are, and whether they produce a lot of ash or fragmented rock material. And this changes through time. So understanding what the information we can get from the system beneath the surface is very important for looking at why a volcano might change its eruptive style through time.
Thank you.
Thank you. Could be a correlation between the behavior of a volcano and the typology of eruption, a correlation between this issue and climate changing. Thank you. Or the climate during in the age of the volcan, so the climate in the 122 before Christ, and the climate now. If a factor that influences the behavior of a volcan.
You mean in the long term or in the short term?
In the long term.
Yeah, no, just want to have a clarification. You mean if the climate change is going to impact on the eruptive style of the volcano, or the vice versa? Is the eruptive style of the volcano affect the climate change? What is your question?
the first one,
Okay.
but I think that it could be possible even the last one.
Yes.
But yes, I'm interested in the first one.
Okay, so I don't think climate change is going to affect the style of activity of a volcano because, as I show, there are a lot of processes that are affecting the style of activity, the composition of the magma, the temperature of the magma. Climate change is going to affect the surface condition, maybe can have some impact of what is happening in the shallower part of the crust, but I doubt this is going to affect the style of a volcano. For sure, the eruption of a volcano can affect the climate. We know because there were past eruptions, that very large eruption that were able to cover with the ash plume, cover the entire planet, basically the temperature of the overall planet went down of 1 or 2 degrees. I think was known as the year without summer. But then the planet by itself recovered its status. So this is transition. So
away from the planet to react in respect of climate change, of increasing of the temperature. An eruptive and explosive eruption. Posso parlare in italiano, poi traducete perché faccio troppa fatica. Cioè, eruzioni altamente esplosive che influenzano comunque, vanno nell'alta atmosfera e influenzano il clima locale e più che locale perché provocano abbassamenti di temperatura, eccetera, eccetera. Possono rappresentare da parte dell'ecosistema una modalità di raffreddamento, cioè il clima, c'è un aumento medio della temperatura adesso in tempi, devo dire, abbastanza brevi, no? Rispetto alla geologia, diciamo.
sì.
Potrebbe essere questo un modo per il pianeta per raffreddarsi e per reagire a questo tipo di cosa che sta succedendo? Secondo voi? Non so che è una domandaccia, però viene da pensare.
Vuoi che posso rispondere?
Sì?
Allora, ci sono dei climatologi che auspicano qualche bella eruzione in modo da invertire il trend degli ultimi anni, soprattutto in termini di correnti oceaniche. Ci sono degli studi che riportano che una sana eruzione come quella dei vecchi tempi potrebbe ristabilire correnti oceaniche che hanno temperato la temperatura, scusatemi il gioco di parole, del nostro pianeta nei secoli passati. Ovviamente non possiamo indurre un'eruzione vulcanica pesante, non ci siamo ancora arrivati. Però questo è il sogno di molti climatologi, quello di avere una situazione che magari in tempi stretti può portare dei problemi, perché avere nuvole di cenere nel cielo vuol dire bloccare la crescita delle piante, vuol dire avere periodi di carestia anche, che però possono ristabilire nel lungo termine situazioni più equilibrate nel clima del pianeta. Ovvio che se non ci diamo noi da fare per primi per cercare di bloccare questo trend, non andiamo da nessuna parte. Non possiamo aspettare l'intervento divino. No, il viceversa. Esatto. È stato provato. Avete visto il grafico che ho fatto vedere? Ci sono state stragi di specie viventi, di animali e piante, a causa di eruzioni. Le eruzioni che abbiamo noi negli ultimi secoli sono niente in confronto alle eruzioni del passato più antico, ma basta pensare ai micenei che sono stati di fatto estirpati dal nostro pianeta da una forte eruzione vulcanica. Si pensa, la forte eruzione vulcanica, parliamo di qualche migliaio di anni fa. Senza andare tanto lontano, eruzioni nel periodo della preistoria che hanno prodotto volumi di materiale anche 100 volte maggiori a quelli delle eruzioni tipiche di adesso. Ci sono delle paleoeruzioni, voi ne sapete qualcosa molto più di me, sono state sconvolgenti rispetto a quelle pur pesanti degli ultimi anni.
I Campi Flegrei, per esempio, l'eruzione dell'Imbride Campana, del tufo giallo napoletano, perciò parliamo di 39.000 anni fa e 15.000 anni fa.
Il problema è che noi non stiamo facendo niente per proteggerci dal ripetersi di queste situazioni. Ne parlavamo prima a pranzo. Quest'anno il Comune di Napoli, assieme alla Regione Campania, hanno organizzato chiamiamoli dei corsi di sopravvivenza, delle esercitazioni per vedere come comportarsi nel caso di una pesante eruzione sia dei Campi Flegrei che del Vesuvio. Si sono presentati in 38 a questo, quindi vuol dire che non ce ne frega niente, vuol dire che continuiamo a campare per quello che succederà, succederà. E questo è un dramma. Altre domande? Any more questions? Okay, so may I just conclude with a few words. I would like to thank the audience for coming here today to join us in this conversation. I would like to thank my colleagues, which have been, I think, really clear in the explanation of how this thing works. And I would like to underline the importance of structures like Sincrotrone Trieste, like Elettra Sincrotrone Trieste, in general, all the large-scale facilities, which are very useful in creating these cooperations between different scientists, mathematicians, physicians, physicists, geologists, and so on, in order to collaborate. And in this field, 2 + 2 usually means 5 and not 4. So this kind of interdisciplinary collaborations, very often fostered by structures like synchrotrons, like neutron facilities, laser facilities, are very important in the development of science in general. Okay, thanks again to everybody. I would like another applause for the speakers. And I hope to enjoy the other activities of Trieste Next as well. Thanks again.